Welcome back to Hardware Security. This week, we will talk about how hardware designers can protect their design intellectual properties from being misused. We will learn what design intellectual properties are and why they are important in modern hardware design. We will show that in addition to law enforcement, there are several techniques available for you to protect design intellectual properties by yourself. These techniques include digital watermarking, digital fingerprinting, integrated circuit metering, and design obfuscation. Through the discussion of this method, we will also see how to make the trade-off among security, cost, and system performance. No special background is needed to understand these concepts. However, the examples we will use require some basics on digital logic design. We will also introduce the concept of graph coloring problems and graph partitioning problems when we use them. According to the Cambridge International Dictionary of English, intellectual property is an original idea which can be used to earn money. Original reflects the novelty of the intellectual property, and the phrase can be used implies the usability of the intellectual property. Examples of intellectual properties are products, technologies, softwares, and so on. Meanwhile, it also states that the person or group who is recognized as having the idea can use the law to prevent other people from earning money by copying it. This law enforcement includes patents, copyrights, trade secrets, and so on. In VLSI design, an intellectual property is a design unit that can be reasonably viewed as a standalone subcomponent of a complete system-on-chip design. It can be any innovation and a technology that make designs better. For example, a place and route algorithm, a power management technique, or a novel design or testing method. These are all considered as design IPs. More tangible examples include microprocessor cores, on-chip memories, PCI interface micros, fully routed netlist, Verilog chip descriptions, and so on. These are also known as virtual components, blocks, cores, or sometimes called micros. Based on their performance and flexibility, design intellectual properties can be categorized into three groups. Hard IPs. They include GDS2 files with test lists and high-level models, customer physical layout, fully placed and routed netlist for a given particular technology library. These hard IPs have predictable performance and most of the time optimized, but they are very, very inflexible. On the other hand, soft IPs are delivered in the form of synthesizable HDL code like Verilog or VHDL programs. They offer great design flexibilities despite the less predictable performance. Examples of firm IPs are placed RTL subblocks and fully placed netlist for generic technology library. They can be considered as a compromise of hard IPs and soft IPs. The driving force behind the intellectual properties is the design productivity gap, the gap between what can be built and what can be designed. This figure is available from Wikipedia. It shows the CPU transistor counts in the past 40 years, following the Moore's law. The Moore's law says that the number of the transistors on a chip is doubled every 18 months. I don't want you to read all the words in small fonts in this figure. What is important is that back in 1971, the Intel 4004 processor has 2300 transistors under 10 micrometer technology. Now, technology has advanced to 20 nanometers, and modern processors have billions of transistors. The capacity of silicon has increased for almost 1 million times in the past 40 years. But designers' ability to do meaningful design with such transistors has not increased at the same pace. This creates the design productivity gap. One of the most effective ways to close the gap is reuse-based design. Starting from the mid-1990s, there are many industry initiatives on IP reuse. In the US, there are Virtual So-called Interface Alliance, or known as VSIA, and Virtual Component Exchange. And the Design and Reuse is the organization in Europe, and IP Highway is the one in Asia. In reuse-based design, IPs are developed not only for use, but also for reuse. Design engineers are forced to cooperate and share their data, expertise, and experience. Design details are encouraged to be documented and made public to make reuse more convenient. But at the same time, this effort has made IP piracy and infringement much easier than ever. Since early 1990s, litigation cases in semiconductor related to IP infringement have been increased very fast, causing an estimated annual revenue loss of billions of dollars. The most dangerous threats of IP piracy came in the form of reverse engineering, chip overbuilding, and counterfeiting. Reverse engineering is the process where a product is taken apart and analyzed in order to improve or duplicate the product. For hardware design IPs, the cost and the skills required for reverse engineering are much less than those to develop the original IP. This gives attackers incentive for IP piracy. Chip overbuilding refers to the scenario when a foundry fabricates more chips than the order and sells those extra copies to the market to make profits. Counterfeiting is the case when a low-quality product or IP is manufactured but sold as a high-quality brand name. The Virtual So-called Interface Alliance has listed the following 4 goals for intellectual property protection. Number 1, enable IP providers to protect their IPs against unauthorized use. Number 2, protect all types of design data used to produce and deliver IPs. Number 3, detect use of IPs. And finally, trace of IPs. In practice, most design IPs are secured by deterrent and protection mechanisms. Commonly used deterrent includes patents, copyrights, contracts, trademarks, and trade secrets. They do not directly prevent IP piracy, but rather discourage the misuse of IPs because the attacker, once being caught, may face lawsuit and severe penalty to recover the financial loss of the IP provider. However, it is the IP provider's task to identify and report IP infringement and find the attacker. Protection mechanisms, on the other hand, use means such as encryption, chemicals, obfuscation, and dedicated hardwares to prevent unauthorized access to the IP. Standard encryptions can be applied to protect the design IPs. For example, both Xilinx and Altera have offered encryption on their FPGA boards. Chemicals can also be integrated into the chip for passive protections, mainly for military devices. When the surface of the chip is scratched and exposed to the air, it will damage the exposed silicon and thus prevent reverse engineering. Meanwhile, obfuscation methods have been proposed at various design phases in order to disguise the design and make reverse engineering much more difficult. In addition, industry organizations have been working on establishing standards for IP reuse and IP protection. For example, Virtual Socket Interface Alliance has published 2 tagging standards to protect hard IPs and soft IPs. Law enforcement is the only means to get back the revenue lost to IP piracy. Encryption and other protection mechanisms make IP piracy more difficult and more expensive. But only the detection schemes such as digital watermarking, digital fingerprinting, and integrated circuit metering can enable IP providers to identify the occurrence of IP piracy. This identification will be the first step towards legal fight against IP infringement. We will focus on these methods this week.